Hi, I'm Brian Risley. I'd like to welcome you to the December meeting of Southwest Florida Astronomical Society. And we're going to go ahead right into our presentation. John McLean has coordinated the presentations. I'll let you introduce our speaker.
Welcome to the 2023 Southwest Florida Astronomical Society Speaker Series. Tonight's speaker is Dr. Olivia Harper Wilkins. Dr. Wilkins is an astrochemist working as a NASA postdoctoral fellow at the Astronomical Laboratory at the NASA Goddard Space Flight Center. At Goddard, she works on the sublimation ice millimeter submillimeter experiment, known as SUBLIME, to study the chemistry of UV irradiated ice analogs. Dr. Wilkins received a BS in chemistry and mathematics from Dickinson College in 2015 and a PhD in chemistry from Caltech in 2021. As a summer intern at Dickinson, she worked at the National Radio Astronomy Observatory, and at Caltech, her research utilized the Atacama Large Millimeter Submillimeter Array in Chile. Dr. Wilkins' talk tonight is entitled Exploring the Invisible Chemical Universe with Radio Astronomy. Please join me in welcoming Dr. Wilkins.
Thank you so much all for coming here today and for having me here. I'm really excited to talk to you about radio astronomy, which is a type of astronomy that's different than what a lot of us are used to. I'm excited to talk about my work in astrochemistry specifically. So my story with astrochemistry, oh no, we had the Turner working earlier and we jinxed it.
Yep, we did jinx it. Let me see if I can get it. There we go.
Okay, great. Thank you. Okay, so my journey to astrochemistry began when I was 7 years old, although I didn't know it then. I knew I wanted to be a scientist when I was really young. Fortunately, my parents let me dig things in the backyard and took me to museums. And my family was also really into going on scenic train rides. And when I was 7, we went to Cass Scenic Railroad, which is in West Virginia. And when I was in West Virginia, driving through the mountains in West Virginia, I saw what looked like a giant satellite dish in the valley on our way to the train. And I remember just being so mesmerized by this giant satellite dish looking thing that I drew it in my sketchbook. And then later, we returned when I was 18 years old to figure out what this satellite dish was. And we found that it wasn't a satellite dish, it was actually a radio telescope. So this is the Robert C. Byrd Green Bank Telescope, or GBT, in Green Bank, West Virginia. And it's no wonder I was so fascinated by this telescope, because it's one of the largest movable objects on land. It weighs 17 million pounds. The dish size is more than 2 acres, so you could fit 2 American football fields on it. It's a really, really fascinating instrument. It's also taller than the Statue of Liberty. And while I was there, I kept hearing about exploring the invisible universe, and I just thought that sounded so cool. So I had this idea of radio astronomy in the back of my mind after that experience. But after I learned about radio astronomy for the first time, I went to college. I was still interested in everything science, so I decided I'm going to study chemistry because someone told me chemistry is the central science, so I don't have to figure out what I want to do now. I'll study chemistry. And then I also studied math because I thought math was fun. But while I was there, while I was in college, I still kept thinking about radio astronomy. So I applied for a summer internship to work at Green Bank and convinced them that with my data analysis skills from my laboratory classes and my math skills, that I was worth taking on and taking a chance on. And I'm really glad that they let me come and be a summer student there. As it turns out, at the end of the summer, I learned about astrochemistry, and I realized that my budding obsession with radio telescopes could be combined with my major. So I was really excited that I could be an astrochemist and still go after these telescopes. So a lot of what I've done in my life since then, many of my career choices have been influenced by telescopes. Another telescope that I visited in the United States is the Very Large Array, whereas Green Bank Telescope is a single dish telescope. The Very Large Array, or VLA, which is in New Mexico, is made up of 27 antennas that work together as one giant telescope with lots of holes in it. So it's called an interferometer. And I forced my family to be obsessed with radio telescopes too. So this is a picture of my son when he had just turned 2 years old, and he loves going to visit radio telescopes. And I'm really proud because now he's 7. And anytime he sees a satellite dish, he calls it a radio telescope instead of calling it a satellite dish. So I'm really proud that he mixes those things up. Some other things about radio astronomy and me in my personal life. After I was in Green Bank, I had a choice before me whether to go abroad or not. So a lot of people at Dickinson College study abroad. I didn't want to study abroad really, but I did want to see more radio telescopes. So I went abroad just so that I could go visit this telescope that's popped up on the screen here, which is the Lovell telescope. And this is the 3rd largest fully steerable single dish telescope in the world. It's located near Manchester in England. On that trip, when I was abroad, I also went to visit the Effelsberg radio telescope, which is the 2nd largest fully steerable single dish radio telescope in the world, and that's located in Germany. And after Dickinson, I went back to Germany for a year, in part because this telescope was there. So I make a lot of decisions based on where I can chase telescopes. So it's really important for me. But this talk isn't just, about me and my role as an astrochemist. It's about radio astronomy and the intersection with astrochemistry. So the story of radio astronomy begins nearly 100 years ago in 1932, and it begins with this man, Karl Jansky. Karl Jansky was a radio engineer for Bell Telephone Labs in New Jersey, and while he was there, they were talking about ways to do transatlantic telecommunications. So his job was to find sources of static that could interfere with telecommunications. So he built this antenna. It's fully rotatable. So you can see in the picture, there are some wheels and there's a track. So Jansky could point this contraption at any point in the sky. And he did that, and he found 3 sources of radio static. He found nearby thunderstorms, distant thunderstorms, and then there was a 3rd category, which was a faint hiss that he only heard sometimes. In some parts of the year, it seemed to follow the sun. In other parts of the year, it seemed to want nothing to do with the sun, and he wasn't sure for a while what it was. But after a year of investigating what this radio signal was, what this faint hiss was, or this steady hiss was, this article came out in the New York Times. New radio waves traced to center of the Milky Way. So Jansky, who was not an astronomer, he was a radio engineer working for a telephone company, made radio astronomy happen, which I think is pretty cool. So after Jansky accidentally discovered radio astronomy as a field, radio astronomy wasn't really picked up, at least not by professional astronomers. You had amateur astronomers who built more telescopes in their backyard, but a lot of radio astronomy was furthered during World War II, when people accidentally, when trying to intercept German telecommunications, ended up intercepting radio waves from the sun. So there was a lot of work that was done in radio astronomy that had nothing to do with astronomers until much later on, which I think is something that's really special about this field. So shortly after Jansky discovered or laid the foundation for this field, astrochemistry was born. And that was in 1937. So this is a picture or an illustration that I did of the Mount Wilson Observatory. This is the telescope dome that holds the 100-inch telescope on Mount Wilson. And in 1937, it was reported by 2 different groups of researchers that this molecule, shown up in the top right corner, which is called the methylidine radical. It's a carbon atom bonded to a hydrogen atom. It was reported that this was found in interstellar space. Just several hundreds of years ago or before this, people still weren't sure that there could be anything in space besides stars and nothing. But now in the what seemed to be voids in space, there was now evidence that we had chemistry that could happen, which is pretty cool. On a side note, this telescope dome is located about 13 miles north of Pasadena, California, where Caltech is. So I didn't go to graduate school because I wanted to be in the shadow of this telescope, but it just happened that way. So even if I'm not trying to chase telescopes, they're chasing me. So it was pretty cool to learn that astrochemistry happened or started right near where I was in graduate school. Since then, radio astronomy has been so important for astrochemistry. So what I'm showing on this plot is on the horizontal axis here at the bottom is year up to 2020. And then on the y-axis here, the vertical axis, we have the cumulative number of detected molecules. And what I want to point out here is that molecular radio astronomy has been critical for the rapid growth in the number of molecules that are detected in space. So you can see here a 36-foot telescope at the National Radio Astronomy Observatory came online in 1968. So between 1937 and 1968, we didn't find many molecules, but suddenly after this telescope comes online, you have this explosion of molecules up through 2020. So on this plot, it's showing you the pattern for the first 240 molecules. This chart is only 3 years old, and it's so out of date. The latest count is more than 300 molecules in space. So the chart keeps going way up to where the O is. So that's really, really exciting, and it's all because of radio astronomy. Said in a different way, we can look at the distribution of the types of telescopes that are used to discover different molecules in space or different chemicals in space. And about 90% of new molecule detections are first made with a radio telescope, showed in blue. The rest are found with infrared telescopes, and then a small portion are found with ultraviolet and visible observatories. The methylidine radical, the first molecule detected in space, was found with an optical or visible telescope. But not many other molecules were found that way. And radio astronomy is really important for finding new molecules. So I'm going to show you an example or some examples of the different types of molecules or chemicals that we can find in space using radio astronomy. So this is hydrogen cyanide. It's very poisonous. It's been used as a chemical weapon, but it's really important in space and quite abundant. And in fact, it's important for life as we know it. So a lot of the amino acids that compose the proteins in our bodies are only here because of molecules reacting with hydrogen cyanide. So not good for us now, but very good for us in the primitive chemical sense. Another molecule is ethanol that we see in space. This is drinking alcohol, so we have booze in space. Another molecule is methanol, which is a simpler alcohol. This is another dangerous molecule. It will make you blind if you consume it. But again, like hydrogen cyanide, bad for us now, but very good for us in terms of primitive chemistry that builds up the building blocks of life. And then ethylene glycol is antifreeze. That's another molecule that we see in space. Isocyanic acid, which here you can see in blue. Sorry, I should have mentioned this. The white balls are hydrogen atoms. The black ones are carbon. Blue is nitrogen, and red is oxygen. So isocyanic acid is an example of a molecule that has a lot of different chemical components. And then one of my favorite types of molecules are ones like this one, which are these long carbon chains. So you have hydrogen, 5 carbons in a line, and a nitrogen atom. And in space, we see the same thing, but with as many as 11 carbons in a line. And these are molecules that are not stable on Earth, but somehow, because the conditions are so different in space, we can find them in space, and you can see them with radio astronomy. So there's some chemistry that looks very familiar to us in space, but then there's some chemistry that makes us question what the laws of chemistry are. So when we're talking about radio astronomy and molecules or chemicals, we're talking about gas phase molecules. So what radio astronomy is sensitive to is these molecules tumbling in space. So as they rotate, or the bonds between different atoms in them rotate, they release energy that happens to be at radio frequencies. So that's what we're detecting, is these very faint signals of molecules moving around in space. Not all molecules can be seen with radio astronomy. You have to have molecules that are asymmetric in at least one direction. So some molecules, like carbon dioxide, which is you have an oxygen atom in a line with carbon and then another oxygen. It's symmetric any way you cut it. So we can't see that with radio astronomy. But for the bulk of these molecules that we're interested in, especially when we're thinking about the complexity that led to life as we know it, we can see them with radio astronomy and study them in the gas phase. And the places where we study molecules are, no surprise, called molecular clouds. And these are our interstellar laboratories. And what I put up here is a phase diagram. So on the horizontal axis, we have temperature. On the vertical axis, we have pressure. And depending on the material you're looking at different combinations of pressure and temperature, that material will be a solid, liquid, or gas. So at cold temperatures, water is ice. At warmer temperatures, it's liquid, and then at really warm temperatures, it's gas. And this is true for any other molecule. But in space, we're looking at things that are at really low pressure and really low temperature. So what this means is that we don't have liquids in interstellar space. So the chemistry that we see in interstellar space is quite different. These molecular clouds take up only a tiny fraction of interstellar space, at least by volume. They're only 1% of the total volume of interstellar space, but they constitute 50% of the mass. And some numbers for you, the conditions in these environments are really extreme. So we have temperatures of 10 to 30 Kelvin. So Kelvin is the scale that most scientists use. 10 Kelvin is negative 442 degrees Fahrenheit. So that's how cold the gas is in these molecular clouds. And these molecular clouds are what form stars. So stars, just like our sun, started at these very ridiculously cold temperatures. The densities in these regions are also really low. So there are 100 to 10 million molecules per cubic centimeter, which might sound like a lot, but the air that we're breathing right now has 10 to the 19 molecules per cubic centimeter. So the threshold for dense in these molecular clouds is 10 to the 17, that's 1 followed by 17 zeros, times less dense than the air that we're breathing right now. And it's amazing to me that any chemistry, anything could happen in something that's that less dense than the air that we're breathing. So in these molecular clouds, most of the material is gas, which is good news for radio astronomers. But that dust is really important because, as I mentioned, there's not a lot of material. And in order for different chemicals to react, they have to be able to run into each other. So when you don't have many molecules in the gas, it's difficult for them to collide and produce new things. So what the dust does is it acts as a catalyst. So what I mean by this is you have different molecules that can be frozen out onto the grain. So this is a representation of carbon monoxide. Again, very deadly to us on Earth, but very important to our celestial origins. If we do something called successive hydrogenation, which just means adding hydrogen over and over again, we get new molecules, bigger molecules. So what happens is a hydrogen atom will come in, it'll hop around the grain until it finds something to bond to. You form something like methanol. And then there are different processes by which it can go off into the gas phase. And then once it's in the gas phase, it's rotating and can be picked up by a radio telescope. So we're looking at the products of these icy chemical reactions and icy chemical conditions. So I'm going to talk a little bit about what I do in terms of radio astronomy and astrochemistry. So we're going to go to my laboratory, which is Orion KL, or the Orion Kleinman Lone Nebula. It's somewhere in the Great Orion Nebula. I'm not sure exactly where, but it's in there. And the work that I'll be talking about today comes from the Atacama Large Millimeter Array, or ALMA. And it comes with support from the National Radio Astronomy Observatory. And then these are people who have helped me along the way in terms of funding the work that I'm talking about today. So most of this is from my graduate studies. But one thing that I really like about Orion KL is it's one of the few objects that I can find in the sky. So I'm not an optical astronomer by any means, so I can't tell you where any stars are. But I can tell you where the Great Orion Nebula is. So it's now winter. We can see the Orion constellation in the night sky. And if you look below the belt, there's a reddish blob. And I'm sure you can see it in Florida because I could see it even in Pasadena and I was right outside of LA. It is bright enough that even with heavy light pollution, you can see it on a clear night. So that reddish blob is where we have the Great Orion Nebula. And as I said, Orion KL is somewhere in there. And this is the closest high mass star forming region to us. So when I say close, I mean it's 380 parsecs away. Who knows what that means? It's 1,300 light years away. So that means that the light particles that we're studying with radio astronomy in this nebula have traveled for 1,300 Earth years to get here. So we're kind of looking not across space only, we're also looking back in time, which I think is pretty magical. So I'm not the first person to study Orion KL. Orion KL, because it's so close, is one of the most studied objects in the context of astrochemistry. This is a picture of the Owens Valley Radio Observatory 10.4 meter telescope. It's a single dish telescope. It's much smaller than the GBT, but it still does some important important astrochemistry research. Here is an example of one of the observations, one of the pieces of data that was taken by this telescope in the 80s. So this is on your horizontal axis here. This is radio frequency. On the vertical axis, we have what we call antenna temperature. This is just signal. So the higher the signal, the more stuff we have typically. And then each of these different peaks in here correspond to a different molecule. So you can see this peak right here, H2CO is formaldehyde, HC3N is a different molecule. This one's called methylformate, and this one is called vinyl cyanide. And then here's our friend methanol right here, the CH3OH. So we know from these types of plots, this type of data, what kind of molecules are out there in space. And not only can we use these spectra, these are called spectra, to learn about what types of things are out there, but we can use those molecules as a probe for things like temperature, for things like density, for velocity. So depending on how the lines are shifted compared to where they would be if they were collected on Earth, we can determine how quickly a cloud is moving away or towards us. We can also learn about whether there are different physical components. So if you look at this HC3N line in the middle, above, like just to the right of 218.3 gigahertz, you can see that it has this wonky line shape. It's very asymmetric. And if you deconstruct those, or that line, the reason it's asymmetric is because it's actually made up of different components. So this is work that my doctoral advisor actually did, Jeff Blake. And what these different curves correspond to are different regions within the nebula. So even with a single dish radio telescope, we can derive things like temperature and abundance for all different types of regions. So they're kind of like, you could think of as the first spectrum being a spectrum of the United States, and then each of these are individual states, for example. So different regions. But when I got to graduate school, I thought it was really cool that from a single dish telescope, we could start to get this spatial information. We could get one set of parameters, one temperature, one density for these regions. But I wanted to know whether we could use a telescope that maps how those parameters change on small scales. And when I say small scales, I mean solar system scales, because in the grand scheme of the galaxy, the solar system is quite small. So I wanted to investigate this because there are lots of open questions about Orion KL that can't be answered unless we can more intimately look at the conditions compared to the chemistry. So, pardon the formatting issue there, but to image Orion KL on solar system scales, you would need a telescope that's 2.5 kilometers across. So if you're familiar with Florida Gulf Coast University, it's about the distance from the start of FGCU Boulevard to Gulf Coast Town Center. In other words, you would need to have a single dish telescope that has a dish area bigger than 1/3 of Southwest Florida International Airport. So you would have a telescope that kind of looks like this on the map. And this just isn't possible. Even if we could afford to build a telescope, a single dish telescope that's this big, it just would not be structurally sound. Something like that, just it's way too big. And I'll show you what some of our biggest single dish telescopes look like. So this is the largest single dish telescope in the world. It's called FAST, or the 500-meter aperture spherical telescope. It's in Southwest China, and that dish does not move. Instead, there is these columns here. These towers have cables suspended from them, and a detector can move along those cables to kind of artificially change the direction of the dish. I already mentioned that the GBT in West Virginia is the largest fully steerable single dish radio telescope, and that's already pushing the limits for what we can do in terms of building these giant machines. That's only about 100 meters across. So for something to be 2.5 kilometers across, you would need to have something that's that has a diameter that's 5 times that of FAST. And FAST is already a behemoth of a telescope, so we can't do that. And then just for scale, that's GPT, just to show it's really big. So instead, what we do is we do something called interferometry. So there's no way that we could have a 2.5 single dish telescope, but what we can do is we can mix the signals from different antennas that are spread out across the field of where we would have a single dish telescope. So we call these individual telescopes just radio antennas. They're in an array. And the size of the effective telescope here is determined by the longest baseline, or the largest separation between any two antennas. So effectively, what interferometry allows us to do, what things like the Very Large Array allow us to do, is have a giant telescope that just has lots of holes in it. So that's how we work around we can't make a 2.5 kilometer telescope. We use arrays like this. So this is the array that I use. This is the Atacama Large Millimeter Submillimeter Array. So Atacama because it's in the Atacama Desert, which is in Chile. Large because it's large. Millimeter, submillimeter because those are the wavelengths of light that this telescope is looking at. And then array because it's an interferometer. It's not just one dish, it's multiple dishes. And in ALMA, you have up to 66 antennas that work together as one giant telescope. There's a cluster of them here called the Atacama Compact Array. Those stay fixed, but for the main array, most of the dishes, they can actually be picked up and moved. So this telescope at different parts of the year has different sizes depending on the needs of the astronomers using it. You can have a telescope that's as much as 16 kilometers across, so very, very big. But this is one of the movers. This is Lore. There's another one called Otto, and they move the telescopes throughout the year for astronomers like me. So I'm going to talk through one of the projects that I did using the Atacama Large Millimeter Submillimeter Array to demonstrate the power of using interferometers. So one question that I wanted to investigate is, what are sources of heating in Orion KL's hot core? So Orion KL being the nebula I studied, and the hot core refers to an early stage of star formation. So when you're forming stars, you start with, starting in the top left of this cyclical diagram, you have a molecular cloud. It's full of gas and a little bit of dust. Those things start to clump together. If you move on, you see there's clumping happening, and then you form these cores in the next stage. So these cores are the seeds of infant stars, and they evolve into what we call protostars. At some point, You're going to have a disk that forms around that star. This disk is where planets form, shown in the bottom. And then eventually you get to a planetary system, much like our solar system. But when we're at the stage of cores, we can think about cores, how they heat. And typically, cores heat internally. So over time, as they're grabbing material from their parent molecular cloud, the inside gets warmer, and then that heat starts to spread throughout the core as it grows bigger. So cores are internally heated, typically, rather than being heated by external sources. So that's usually what happens. But with Orion KL, it's not clear that this is the type of chemistry or the type of astrophysics that takes place. There's been suggestions that that maybe it's externally heated, in part because no one has ever seen a star or a protostar there. So the assumption is, well, if there's a star internally heating this core, then we should be able to see it with a radio telescope, but we don't. And then there's also this molecule called HC3N that can sometimes trace very hot gas. And it's found that some of this hot HC3N forms this shell around the hot core. So it's thought that maybe that's indicative of hot gas outside being transferred into the hot core, so an external heating there. But there are also plenty of people who say, nah, it's actually internally heated. Part of it is because the hot core chemically looks like a hot core. It looks like any other hot core that's internally heated in the fact that it has lots of hot molecular molecules. So it meets all the characteristics except for having a star. And then some people point out, well, maybe there is a star, but if there's a circumstellar disk, if we're looking at it edge on, it might be blocking the starlight from being seen by a telescope. So just because we don't see the star doesn't mean it's not there. So that's been something that's been debated for a few decades, and I decided I wanted to get in on this argument. I'm on the internally heated side, and I'll try to convince you or show you why I think that the hot core is internally heated using radio astronomy. So what I did is I looked at temperature on slightly different scales. So as I mentioned, ALMA, depending on, or the size of ALMA depends on the largest baseline, the biggest separation of any two antennas. And one thing that's really nice about when you use an antenna like ALMA is you can write in your computer code that you only want to use certain antennas. So I could artificially make the telescope smaller when I was analyzing my data. So I had my regular old data in what we call a large beam. And then, that gave me a small beam. And then the smaller telescope gives you a larger beam. It's backwards and confusing. But what I said is that if you have higher average temperature, or if the temperature on any given pixel in the cloud or any different spot on the cloud has a higher temperature on the smaller scales, that's indicative of internal heating. So that means that when you're looking at it on larger scales, you still have that warm material there, but it's being diluted by colder gas that's surrounding it, artificially lowering the temperature. On the flip side, if you have a higher average temperature on larger scales and a smaller temperature on the smaller scales, that's indicative of internal heating. So when you look at a spot in the cloud, you get one temperature. And then if you look at the gas surrounding that, if that raises the temperature, that's a sign of external heating. So that's how I approach this. So I used observations with ALMA of this molecule called acetonitrile, which is CH3CN. And I looked at a specific flavor of acetonitrile that gets excited at warm temperatures. So it's very active at warm temperatures. And what these maps are showing is what I call delta T, or the difference in temperature. And what these maps show is I took the temperature on large scales and I subtracted the temperature on small scales. So this means that for positive numbers or redder numbers, where you have a higher temperature on the large scale, that's indicative of external heating. Negative numbers or blue patches in the maps show the opposite, or internal heating. In the center is just the regular old difference. And then with these observations, we have lots of uncertainty. So I'm just showing you on the right and left kind of the boundaries for what I thought these maps should look like. And what you can see, but at the edge or at the endpoints of these arrows, that's the hot core, it's consistently blue. So based on these observations, it seems that the hot core is in fact eternally heated. So that's some of the cool stuff that, or hot stuff that we can do with chemistry and radio astronomy. Another thing that I was interested in is, okay, so Orion KL has been studied over and over again. What about other massive star forming regions? There's only a handful of massive star forming regions that are studied in astrochemistry, Orion KL being one of them. Another one is Sagittarius B2N, which is a star forming region in the center of the galaxy. But what about the stuff in between? I wanted to address this problem, which is that much of our understanding of star formation comes from nearby low mass star forming regions like Perseus molecular cloud, illustrated here, and a handful of exceptionally molecule rich high mass sources. So when I say exceptionally molecule rich, they're kind of easy targets to find. So if they're really easy to find, if they're teeming with molecules, how do we know that they're representative of all high mass star forming regions? So what I did is I set out to look at what we call the molecular ring. So this is a graphic showing what the Milky Way would look like if you could look down on it. We are located near where this house is. And the molecular ring is this region shown by the blue ring at radii of 4 to 8 kiloparsecs from the center of the galaxy. So I think that's 13,000 light years from the center of the galaxy to 26,000 light years from the center of the galaxy, which, like, I can't comprehend what that means, but it's just really far from the center of the galaxy, and it bumps up right to us. We're right on the edge of the molecular ring. And this ring is home to most of the molecular matter in the Milky Way. We think up to 70% of the molecules that are in our galaxy are found between these gold circles in the Milky Way. But we don't really study chemistry there. And I think that that's a problem. We should be studying chemistry where chemistry happens most abundantly. So I set out to try to address this problem by using ALMA, and specifically I use the Atacama Compact Array. So as I mentioned earlier, the Atacama Compact Array, or ACA, is a subset of ALMA antennas that don't move. So that means they can't give you as big of a telescope as the main ALMA, but they're still spread out more than your typical single dish radio telescope. So they still do better than something like, say, the GBT. So I used this as part of a pilot study. I could see the clouds I was looking at on angular resolutions of 10 to the 4 to 10 to the 5. So that's 10,000 to 100,000 AU, which I can't comprehend what that means. But earlier when I said I was looking at solar system scales, that was about 100 AU. So this is 1,000 times more than that, potentially. But an AU, one AU is the distance between Earth and the sun. But the point is that we're able to look at individual clouds. We're able to separate the chemistry between individual clouds on the scale. And I used the ACA to investigate 11 clouds selected from a sample of its cutoff, but I think it was 487. So I down selected by saying, okay, I'm only going to look at the densest clouds, because we know, thanks to astrochemistry, that stars form in regions where you have the densest gas. So I looked for places where I had a threshold for what density meant. I also looked for clouds that could be observed in one shot with the ACA, because observing time is precious. And I thought, if I have to use the ACA twice to observe the same cloud, no one's going to give me time to do that. So I'll just pick the easy targets. And then the last thing I wanted to do was make sure that my targets were in the molecular ring. So when I used all of these criteria, I got down to 11 giant molecular clouds. So when I looked at these molecular clouds, I found some really cool chemical stock rings. So I detected nearly 100 millimeter emitting regions. So this means dusty regions. They might be places where you have cores that are forming. You might just have dense gas that isn't quite ready to start forming stars. But only about 15 had chemistry. And we found 17 molecules in our survey, which was, we weren't looking for anything in particular, but we found 17 things, and they contain the elements hydrogen, carbon, oxygen, nitrogen, sulfur, and silicon. And here's just a selection, or here's showing what the different molecules would look like. So I want to point out a couple different molecules. First, methanol, which I keep bringing up. I love methanol. It's a tracer of complex organic molecules. So that means if you have methanol, there's a good chance that you're forming prebiotic molecules in that environment. So that's the type of study, or that's the type of chemistry that I want to study. We also have carbon monoxide, and specifically heavy carbon monoxide. Typically, oxygen has a molecular weight of 16, but sometimes it has a molecular weight of 18. So this heavy carbon monoxide is a tracer of dense gas. So that's a good, if we have carbon monoxide of this flavor, it's a good indicator that we're seeing where a star is going to form. And then the last thing I looked at was silicon monoxide, which traces protostellar outflows. So when you have a baby star that's forming, it ejects these jets of very hot material, and you see lots of sulfur and silicon bearing molecules there. So I wanted to see what some of the chemical patterns look like. So I'll just show you some of the maps that we can make of the chemistry in these regions. So these maps show methanol in green and the C18O in gold. And I just want to point out a couple things. So in the center, the bottom center panel, you can see, or maybe not see because it's pretty dark, but hopefully you can see that those signals overlap really well. So the methanol and the dense gas tracer line up pretty well. But then in other places, like the top left panel, these things are, they're offset from each other. In the top middle, we see that there's lots of C18O everywhere. It's very extended. It covers the whole dark patch of dust that's shown there. But then we have two of what we think are hot molecular pores that have never been seen before. So what's exciting is these molecules have never been detected in these environments before. And that's because previously they were observed with single dish telescopes, and all of the chemicals were kind of blurred out. There wasn't enough to make a strong enough signal for them to be seen. But thanks to the ACA, we can see these different molecules there. Some other maps are shown here. So again, our methanol is in green. That's a tracer of the complex organics. And then silicon monoxide, a tracer of protostellar outflows, is shown in yellow. And again, we can see there are some places like in the bottom left panel and in the bottom middle panel where the molecules overlap really well. But then up in the top right, they're offset from each other, and I have no idea why. And that's something I hope to investigate in the future. And same thing with the bottom right. So the point is that with radio astronomy, we can see that in these different regions, there's a diversity of chemistry that's happening. And that means that there's some exciting things to be learned about star formation in these regions and the chemistry that evolves alongside that star formation. So I'm going to end by summarizing what I hope you take away from this today, because I know that this was a lot about astrochemistry. But I hope that after today, you are convinced that molecules are powerful tools for studying the structure of stellar nurseries. I also hope that you appreciate high resolution imaging because it gives us a new but complementary view of even some of the most well-studied objects like Orion KL. And that with high resolution imaging, we can expand the roster of interstellar laboratories so that we can get better statistics and understand chemistry at different distances in the galaxy. So that is all I have today. For those of you who are here in the room, I do have a limited supply of NASA stickers that I would love to hand out. So make sure you come say hi to me. But thank you so much for your attention, and I will gladly take any questions.
Thank you. I think Tom said that those who are remote can try and unmute themselves and see if you can talk if you've got any questions.
This is in interstellar clouds, right? Not in stars.
Yeah, so the question is, all of this is in interstellar space and not in stars. Yeah, so this is an interstellar space, but it's the interstellar space where stars are forming. So it's bridging that gap.
Yeah. Gas and dust. How big are the particles? I mean, gas molecules are completely individual, as I understand it. Gas molecules are completely individual, and dust is solid, and so some have accreted together. Is that a function of temperature or of the type of molecule it is?
Yeah, okay, so the question is, so dust, what size is it? Does dust accrete together? And as it accretes, what is that a function of? Is it of temperature? So dust, we think that interstellar dust, based on radio observations, is as fine as talcum powder for the most part. So it's something that you would be able to see, but it's very fine. And what it's made, we're not sure what it's made of. Some people think that it is basically ash or soot from a star that died. Other people think that it's made up some other completely different way, whether it's dominated by silicon minerals or carbon minerals, we don't know. So as dust aggregates, especially in the protoplanetary disk. So you have a star, it forms a disk, and then you have dust particles that plow into each other, and they carve out rings in the disk, and that's what forms planets. We don't really know what triggers that to happen, or at least I certainly don't know. There's a whole area of astrophysics that tries to figure out what happens between having what we call pebbles. So eventually the dust grows to the size of a pebble. And then there's some magic that happens, and they're the size of planetesimals or baby planets. And we don't know how that happens. So some of it has to do with stellar wind that pushes molecules together. It has to do with pressure. So you might have gas that kind of slows things and backs them up so that dust particles are running into each other. As far as I know, temperature isn't so much a factor in that process. But there's a lot that we just don't understand about dust. So there are people who dedicate their lives to studying dust to answer those exact questions.
One from the field?
Yeah, so it also can look at dust. It's called continuum. So it can get some thermal information from the dust, but it's not the same type of thing. But when you're looking at individual molecules, it's only gas fins. Does someone online have something to add to the dust?
Somebody up there cut in.
Yeah, can you hear me from the field?
Yeah, we hear you.
I have a question. Are you
Yeah.
seeing radical species?
Yeah,
And
so
and
go ahead.
are you finding the ratio of radicals to earthly stable molecules increases as the density of the gas goes down?
Yeah, okay, so we do see radical species out there. So we see, so I mentioned these weird long carbon chains that have hydrogen on one end and nitrogen on the other. We also see these weird long carbon chains that just have a hydrogen on one end, and they're radical species. And then there are other radicals as well. So the methylidine radical was the first molecule ever detected.
Right.
I don't know exactly what the trends are with radicals. You'll see radicals in places where you have higher radiation. So, for instance, going back, thinking about disks again. So on the surface of a protoplanetary disk, you have lots of UV light that hits that surface. You have lots of X-rays, X-ray radiation that hits that surface. So you have lots of radicals and also ions that are on the surface of the disk. Whereas internal to the disk, where things are shielded from that radiation, you have all what we call neutral species, so no radicals. But from my understanding, I mean, I don't know what the trends are with density, but I think the presence of radicals has more to do with the presence of strong radiation.
Yeah, to form them, but if the lower the density of the gas, they're not going to find anybody to quench themselves.
Oh,
So
I see what you're saying.
yeah, I mean, there's you're 12 orders of magnitude below atmospheric pressure, right?
Yes. Yep.
And that's in your dense regions.
Yeah.
So, you know, you probably don't have the sensitivity to detect it, but in interstellar space, these things ought to float around as radicals because they don't have anything to react with.
Yeah. So that's still kind of that's something that isn't, or the gas phase radicals are something that have been more recently explored. So we also form radicals on ices and on the surfaces of dust grains. And those radicals, when they warm up, even if they're going into less dense gas, when they come right off the grain, the gas is relatively dense. Like it's not homogeneously diffuse. So we don't think that when you start from solid state chemistry that you have radicals that end up in the gas phase. But I think you're absolutely right that if you have gas phase radicals in diffuse gas, it would make sense that it would be inversely proportional to density. I think you're absolutely right there.
Thank you.
Yep, thank you. Yeah, in the back.
So on this KL region you're looking at, what percentage of that gas cloud are these molecules in terms of mass that you're interested in? Because there's got to be free hydrogen and stuff going around, right?
Yes. I do not know the answer to that question. It's a very good question. So the closest thing I can give you, which is not exactly related to that, is that molecular hydrogen is the most abundant molecule in space. And it's about 10,000 times more abundant than carbon monoxide, which is the next most abundant molecule. And then everything else is way less. So I don't know what the mass fractioning is, but most of it is hydrogen.
Right. So it's a small percentage then,
Yeah.
right? Okay, that was it.
Okay.
And then the other thing, that KL region, how does that relate to the whole nebula? You know, most of the people here know what the Orion Nebula as a whole looks like. Do you know what portion of it you're talking about, the KL region?
I honestly don't. This is where I'm going to say I am more of a chemist.
Okay.
Which is one of the nice things of being an astrochemist. Whenever I don't know, I just say I'm the other thing. But yeah, I'm not sure. So in the Orion Nebula and in the Orion constellation in general, you have places where massive stars have already been formed. You have regions elsewhere called the Orion Bar. I don't know if that's part of the Great Orion Nebula or not, to be honest. But that's a region where you have lots of UV radiation, more so than in Orion KL. So I don't, but yeah, I can't answer your question.
All right. Thanks.
But great question. Thank you.
Anyone else in here? Okay. Linwood.
You talked about the observations coming from the very low end of the temperature spectrum or temperature pressure graph. Very cold, very low pressure. It seemed like you implied they formed there. How do you know they formed at that part of the temperature pressure spectrum, as opposed to shortly after maybe they're ejected from novae or some other way? How do you know that that's the conditions under which they formed? Can you tell that in some way?
Yeah, totally. So You have molecules that form in the late stages of star formation, or I'm sorry, in the late stages of stellar evolution. So around dying stars, we do see molecules. But for the most part, after a supernova, most of the molecules would be obliterated. As far as we know, there's lots of energy to dissociate the molecules is the assumption. And I think that's based on models. But I don't deal with late stage stellar evolution, so take that with a grain of salt. But the reason why we know that these molecules form at these low temperatures are based on a combination of observations. So just from observing these regions, we can look at snapshots of different stages of star formation. And in really cold regions, we don't see anything there. In the clouds, what are they called? I can't remember, but there's another kind of cold cloud that's not molecular. I think it's cold, neutral, atomic. We don't see molecules in those regions, and those are what come before we have the molecular clouds. So by looking at what comes before a molecular cloud, we know that there aren't molecules there. And then we also know that molecules form under these conditions based on computational models, but also experiments. So most of my work right now at NASA is to make cosmic ice analogs at 10 Kelvin at negative 442 degrees Fahrenheit, give it a sunburn and see what happens. And from experiments like that, we see the molecules that show up in interstellar space. And so those three pieces together, the observations, the models, and the experiments all seem to suggest that most molecules, not necessarily all, but most molecules form in these lower density, very cold regions. But there are people who think, or researchers who study molecules that could survive a supernova explosion. So I mentioned that dust could potentially be stellar soot after a star dies, that it releases these carbon-rich materials. So that would be an example of a molecule that forms from a supernova. Yeah, so that's the pieces of that. Yeah.
Any other questions from in here? Okay.
Somewhat related to that, you mentioned early on that all these molecules are in a solid state. At what point or how do they become gases? Is it because they become associated with some nearby star, or?
Yeah, that's a great question. So there are a couple different ways by which you can go from the solid state molecules to the gas phase. So at really cold or at warmer temperatures, you can imagine just like if you have an ice cube and it melts, it changes its physical state. Same thing if you're around a star and that star is warming up, your ice is heating up, it's going to, I said there's no liquids, so it doesn't evaporate or melt, it sublimates. So it goes from a solid to a gas. So that's one way, is through, we call that thermal sublimation or thermal desorption. So that transition from solid to gas. But in colder regions, this has been a real mystery because there are some places in space, like as cold as 20, 30 Kelvin, which is typically things like methanol will sublimate at temperatures of like around 130 Kelvin, more or less. But we still see methanol at like 100 Kelvin less than that when it should be frozen. So some other ideas are that you could have cosmic rays, which are highly energetic particles that hit the dust grains. They locally heat it or inject energy on a small scale and eject things off. It's also thought that if you have molecules that bombard a dust grain, same thing, they're injecting energy onto the grain. So you have local spot heating that causes those molecules to get pushed off. So some people think it's the spot heating where maybe you have some of that thermal sublimation, but other people think it's maybe you could have sputtering, where if a cosmic ray hits, it's the energy kind of, I think of it as the energy goes through the brain and pushes what's on the other side off of it. But that's something that people are trying to figure out is what are these dominant processes in these regions. But for the most part, the short answer is they warm up.
Anyone else? How
Can
about
you,
online? Anybody?
can you hear me?
Yeah, we hear you.
Yes, Peter. At any rate, I noticed that there's a lot of organic chemistry in these molecules. You have the carbons paired with, well, they have triple bonds, double bonds with oxygen. And I would have, thought it was more elemental, but these are, actually organic molecules.
Yeah, it's I think that's something that surprises a lot of people like in the field, just the prevalence of organic molecules. So I forget what percentage are organics, but in terms of what we call complex organics, we call complex organics anything that has 6 or more atoms. On Earth, we call those starting reagents for actual complex organics. But in space, things like methanol, we call complex. And those types of molecules take up about 1/3 of the types of molecules that are out there so far, or 1/3 in terms of the number of different molecules that have been detected. But then we also see lots of smaller organics. So I don't know the exact number, but a significant proportion, and it might be half, are organic. We do see some other molecules that, like, I'll be perfectly honest, like the molecules that I showed, they're pretty biased because I love the organic chemistry. I'm a chemist. But you have people, other researchers who study things like things with magnesium in them or calcium, things that are, only 2 atom molecules. So I definitely gave a biased perspective, I'll admit that. But there are still lots of organics. So I'm glad that you picked up on that.
Anyone else?
How is it that these large or complex organic molecules exist in interstellar space, I believe is what you said, but not on Earth? I know you stated that some could be protected from interstellar radiation if they're in clouds, but that still begs the question, why not on the Earth's surface, which is also protected largely from interstellar radiation?
Yeah, so I think, so from my understanding, this is a matter of density. So you can form things like HC5N, so these long carbon chains, HC11N, so that's hydrogen, 11 carbons in a line, and nitrogen. Not stable on Earth, but you can form them in the lab under, I don't, that's something that I'm not familiar with how they do it, but they do it. But what the general understanding is that when you have these molecules that aren't stable on Earth, when they're out in space, it's just because there isn't enough stuff to run into them. So on Earth, these things that have all these triple bonds would quickly react with things like water or with hydrogen, and that would break apart those triple bonds. But you just don't have as much stuff running into them in outer space or in interstellar space for that to be a problem. But that's still very much an open question. So that's the current hypothesis. But in all honesty, we really don't know why they exist in space, because as far as we're concerned, they shouldn't, but they do. So there are people who work on that, but we haven't gotten to an answer yet.
Thank you.
What's the definition of organic? So as coming from a chemistry background, when I say organic, I mean something that has at least 1 carbon hydrogen bond. So that's like the very basic definition I use. But when you're talking about astrophysical chemicals, it just so happens that all large molecules are also organic. So they all have that at least one carbon hydrogen bond. So that's the basic definition that I use.
So carbon monoxide is not.
Correct. Carbon monoxide is not organic. Carbon dioxide is not organic, but methanol is. I'll just leave it at that. There's some argument about what the definition should be, but I go with the carbon to hydrogen. Thank you. I appreciate the validation.
All right. Anybody else? Okay. Yeah, I do want to thank you, Olivia. Now you're going to be at my wife's library tomorrow. What's the talk
Yeah,
that you're giving then?
Yeah, so I'm giving a talk on JWST, or the James Webb Space Telescope, T plus 2 years. So I'll be going over the planetary science that JWST has done over the last 2 years. Also talk a little bit about the launch and the telescope, and some of the first images in case people haven't had a chance to see them or would like to hear. So
What time is that?
that is at
2.
2 o'clock
Okay.
tomorrow.
Yeah, for those of you who don't know, the North Fort Myers Library is on Business 41, just north of Bayshore Road, on the left-hand side. So,
Yeah, thanks for the shout out.
yeah, thank you. A very interesting talk.